So on Thursday, we ended off and we had gone over a few more position versus time graph questions. Okay, so I want to quickly review the stuff we can get from a position versus time graph. Okay, so for example, if I asked you, what is the position of the object at time 2 seconds on this graph? Could you tell me? Yes, you could, because this is a graph of position versus time. And I would have to just look at time 2 seconds, okay, which is right here, okay, and go over to there and say, oh, the position of the object is -4 meters. Right? So position and time are the two things that I can read directly off the graph. Okay? I could also ask that in the reverse and say, what is the time when the object is at a position of +6 meters? And you would go, oh, here's where it's at a position of 6 meters. That happened at 6 seconds. So there we go. All right? So those are the two things we can read directly off the graph. Since this is a graph that shows position and time, I can use it to calculate displacement. Right? And the way we calculate displacement is we take the final position and we subtract the initial position. So if I was to ask you what's the displacement between 0 and 3 seconds, okay, you would look on your graph and go, all right, at 3 seconds, the object is at -4 meters. Okay, so that would be my final position, and at time 0, it's at 0, so the displacement there would be -4 meters. Okay, so I can get displacement off the graph using that. I can also get the total distance traveled from a position versus time graph by simply figuring out how far it goes in each section. So in this section of the graph here, it goes 4 meters from 0 to -4. Okay, since distance is scalar, I don't need the direction. During this part of the graph, it doesn't move. Okay, it stays at one spot. And then it goes from -4 to +6, which is 10. So my total distance traveled would be, add them up, 4 plus 10 is 14 meters, which was one of the things we had to do for this question. Ringing a bell? All right, last thing I can do. If I'm asked for the velocity of the object, I can use this formula. Final position minus initial position divided by time, okay, which really is this formula. I would have to use that method for this graph because this graph has many sections. Okay? If I was given a graph that looked like this, okay, and told that y equals 5.1x plus 2.5, what's the velocity on that graph? This would be important because you have a lab that asks that. Tomorrow, do. Which part of that equation represents the velocity of the object? It's the slope. Okay, let's quickly review. See that other formula that's just to its left? V equals final position minus initial position divided by time. That's the slope. Okay? If I am looking at this graph, this is my initial position. It's also B. Right? This would be my final position. Actually, anywhere along the line could be my final position. So, okay, that would be Y. And this would be X. So M equals Y minus B over X is the same as saying my final position minus my initial position divided by time. Remember, we went over that last week. We said that's where V equals D over T is derived from. It comes from the graph. Okay, that's going to be pretty important for your lab that's due tomorrow. Okay, for this graph, because it's irregular, I can't use the slope because there isn't one. Okay, there's many different sections. I can still use this formula, however, because I know the final position is 6 and the initial position is 0 and the total time is 6, and I would get 6 minus 0 over 6, which is 1 meter per second, and it's positive. Okay, is that ringing a bell? If it isn't, well, we're working on it again today, so you'll get a bit of a refresher. Everybody with me there? Okay, those are the things we can do from a position versus time graph. Okay, we didn't do this one because it was too involved. Okay, but I think at the end of the day, I was asking you to draw all the shapes on it for the second part of the question. But let's go back to the first part of the question here, where it asks us to calculate the acceleration between 12 and 14 seconds. Last week, I introduced this formula. Acceleration equals final velocity minus initial velocity divided by time. Does that look a lot like the one we just used? Right? We just used velocity equals final position minus initial position divided by time. Well, this is a velocity versus time graph. So with that formula, also be equal to the slope of a line on that graph. I would think so, because B would be my initial velocity, Y would be my final velocity, and X would be time. Yes? Okay, remember we said on Thursday that the slope represents something different on every graph, but it isn't hard to figure out what it represents simply by plugging in. Okay, if I'm solving for slope, okay, I'm just going m equals y minus b over x. Well, what's on the y-axis? Velocity. Okay, so b would be my initial velocity. What's on the x-axis? Time. Oh, it's change in velocity over change in time. That's acceleration. You've got to be able to do that. Okay, set that up on any graph. Okay, for this particular graph, because we don't have a single straight line, the slope method's not going to work. But this method will. Okay, so between 12 seconds and 14 seconds, can I find my initial and final velocities? Because that's one of the things I can read directly off of this graph. So at time 14 seconds, my final velocity will be negative 6 meters per second. Okay, my initial velocity at time 12 seconds is 2, and between 12 and 14 seconds is 2 seconds. Everybody okay with what I've done there? All right, so I've got negative 6 minus 2, okay, well that's going to mean negative 8, right, divided by 2 is going to be negative 4, and what are my units for acceleration? So this is in meters per second, and this is in seconds. If I divide meters per second by seconds, I get meters per second squared. Meters per second squared, or meters per second. Okay? We usually just write it meters per second squared. Okay? So what that means is during that section of the graph, the object is changing its velocity by negative 4 meters per second every second. Okay. The total displacement over the whole trip, that's the part that's going to take a while. Okay? One of the things we know about a velocity versus time graph is that we can use this formula, section by section, to calculate the total displacement. Okay? How far does the object go between 0 and 2 seconds? Zero. How do I know that? Because the velocity is 0 for 2 seconds. Last time I checked, just standing here won't get me anywhere. Okay? That's exactly what that object is doing for the first 2 seconds. It's not moving. Okay? And if you were kind of remembering, we said it's kind of like calculating the area between the line and the x-axis. Is there any area between the line and the x-axis here? The line is on the x-axis, so there's no area to calculate. All right, if I want to calculate the area under the line, there's a whole bunch of shapes I've got to draw. Some rectangles and some triangles. Okay, I'm going to give you guys a few minutes to get them all drawn. Okay, so maybe make a rough diagram of this or something like that, okay, so that you can get the shapes all drawn. We need right angle triangles and rectangles in order to get the total displacement here. I'll give you a few minutes, then I'll draw them, okay, and see if we draw the same ones. Let's have a look at the shapes we're going to have to calculate the areas of. So I'm going to have this triangle here and the triangle next to it. Okay, they're different. Okay, the rate of change of velocity on each side of that triangle is different, so they have to be separate triangles. Okay, and then I'm going to have this one, and then I'll have the rectangle in between those two triangles there. Okay, and then I'm going to have this really, really tall triangle. And a rectangle and a triangle. And that one. Okay, those would be the shapes I would have to calculate the area of if I was going to calculate the total displacement of this object. What do I need to keep in mind for many of those shapes? Their areas will be and it would apply to all of these ones and these two. They'll be negative, right? I mean, the height of this triangle is -3. I have to keep that in mind. That means the object's going backwards. Okay? Displacement's a vector quantity, so I've got to keep that in mind. All right, I'll give you a few minutes now that you know what the shapes are. Okay, get those areas calculated, and then we'll check them together here in a few minutes. Okay, let's have a look at these here. So, for this triangle here, okay, we have a base of 3 and a height of -3. Okay, so -3 times 3 is -9, but it's a triangle, so divide that by 2, and we've got -4.5 meters for that triangle. Okay, this triangle here has a base of 1 and a height of -3. -3 times times 1 is -3, divided by 2, this one is -1.5 meters. Okay, then we've got this little triangle up above, base of 1, okay, height of 2, 2 times 1 is 2, divided by 2 is 1 meter. Okay, and then I've got this rectangle that has a base of 1, 2, 3, 4, 5, okay, and a height of 2, 5 times 2 is 10 meters. Then I've got this little triangle that only has a base of 1/2 of a second and a height of 2. 2 times 1/2 is 1, divided by 2 is 0.5. So that one's 0.5 meters. Okay, then I've got this triangle here that has a base of 1.5 and a height of -6. -6 times 1.5 is -9. It's a triangle, divide by 2. We've got another triangle with an area of -4.5 meters. This triangle here, okay, goes from -2 to -6, so it has a height of 4 and a base of 2. 4 times 2 is 8, divided by 2 is 4. So that one's -4 meters. This rectangle has a base of 1, 2, 3, 4, and a height of -2, so it's -8 meters. And then this triangle here has a base of 1 and a height of -2. -2 times 1 is -2, divided by 2 is -1 meter. So now I have all of those areas. Okay, now I can add them all together. All right, so we'll have -4.5 plus -1.5 plus 1 plus 10 plus 0.5 plus -4.5 plus -4 plus -8 plus -1. All right, so we got -12 meters as our total displacement. Would I ever give you one like that on a quiz or a test? I wouldn't. That's got way too many calculations in it. I'd give you one that had like 2 parts or maybe 3 parts at the most. Okay, so you had to do like 3 area calculations just to show me, hey Coder, I know how to do this. Not, hey Coder, I can draw 12 different shapes and calculate their areas and then add them up for you. Yeah, I don't need you to do 12 to show me you know how to do that. Okay, 3 will be lots. But expect that I'll ask you to do that skill. Just not that many times. Everybody with me there? Okay. All right, so we talked about these ones on Thursday. I think that was actually the last one we did. So here's one that's simpler. It's like what we just did, but simpler. Okay, so I want you guys to give this one a try here. It's asking you to calculate some acceleration, some displacement, average speed over the whole trip, which means you'll need the total what? Distance. You'll need the total distance for that, so you'll have to calculate all the areas again. Okay, and the acceleration between 2 and 4 seconds. All right, so maybe make yourself a quick drawing of that, okay, so that you have it and you can get started. I'll give you about 8 or 10 minutes, and then we're going to go through it together. Okay, so really take your time with this one. Okay, make sure you're practicing the skills involved with these velocity versus time graphs. That was on a quiz a couple of years ago. Okay, so first part of the question, part A, wants to know the acceleration between 7 and 9 seconds. So that means starting right here and going to here. Okay, how do we calculate acceleration? Parker? Position? Velocity, right. Okay, so we got acceleration equals final velocity minus initial velocity divided by time. So my final velocity is at time 9 seconds, 0. Okay, and at time 7 seconds, it's 3. All right, that takes 2 seconds because between 7 and 9 is 2. Everyone okay with that so far? Okay. So I got 0 minus 3, that's going to be negative 3 over 2, so that's going to be negative 1.5 meters per second squared, or meters per second. Okay, everybody all right with that? Now, the total displacement between 0 and 7 seconds. So here's where 7 seconds is. All right, so there's that last shape that I'll have to calculate at the end of all of this. Then I'll have like a big rectangle there, and a rectangle and a triangle. I think those would be my shapes. Everyone all right with that? If you drew yours slightly different, there's like one other way you could have drawn it with one long rectangle all along the bottom. That'll work too. Okay. So if I'm calculating the displacement here, I've just got to get these areas. So this triangle is 1 times 1 divided by 2. So that's 0.5. Okay, this rectangle here is 1, 2, 3 on the base and 1 high, so that's 3 meters. Okay, this triangle here is 2 high by 2 on the base, so 2 times 2 is 4, divided by 2 is 2 meters. This big rectangle here is 1, 2, 3 on the base and 3 high, so that's 9 meters. Okay, and that's up to 7 seconds now, so 9 plus 2 is 11, plus 3 is 14, plus 0.5 is 14.5 meters. All right, everybody okay with that? Okay. If it wants to know the average speed over the whole trip, average speed is total distance divided by total time. Okay, I have one more triangle if I'm going to get the total distance, yes? Okay, so this triangle here is 3 high by 2 on the base. 3 times 2 is 6, divided by 2 is 3. So add another 3 to that, that's going to be 17.5. So 17.5 meters is the total distance, divided by 9 seconds. Okay, should give me 1.94 meters per second as my average speed. Okay, everybody all right with that? Okay, and then the last one is pretty straightforward. The acceleration between 2 seconds and 4 seconds. So that's this part of the graph right here. Okay, so again, we'll have our VF minus VI over T. So VF is going to be 3, VI is going to be 1, and that takes another 2 seconds. So 2 over 2 is 1 meter per second squared, and it's positive because it is speeding up in a positive direction. Okay. Now, here's something I've done on tests before. I have asked, with a graph that looks just like that, this question. What is the acceleration between 4 and 7 seconds? How many marks would that be out of? Notice I didn't say calculate the acceleration between 4 and 7 seconds. I only asked what is the acceleration between 4 and 7 seconds. How many marks would that be out of?
1.
1. Why?
Because there's no acceleration.
Because there's no acceleration between 4 and 7 seconds. You would be surprised when I ask that question, how many people show me at least 4 marks worth of work that's all wrong. Okay? It's crazy, but they do it. I don't know how. I don't know where they get the numbers from. But they show me 4 marks worth of work for 0. Okay? I mean, I could show 4 marks worth of work, go VF minus VI over T, and go 3 minus 3 over 3. That's still 0. Okay? But I don't have to do any work to know that. I just have to look at the line and go, the velocity's not changing. And the definition of acceleration is a change in velocity, so it's not happening. Okay? And it's 0. Does everyone follow me there? You would be surprised how often I try and trick people with that. And how often I succeed is the sad part. Okay? So don't get caught on something like that. That's a checking your understanding question, not a checking your calculations question. Okay. I would like you guys, as some practice here, in your digital workbook, on the bottom of page 7 is this graph. On page 8 are the questions that go along with it. Okay? They start out really, really easy. Right? It's just asking you, what's the position at this time, at this time, at this time? Okay? Well, it's a position versus time graph, so that's pretty easy. You just have to read it off the graph. Okay? And then some calculations of total displacement from 0 to 2, 0 to 4, 0 to 11 seconds. And then a couple other displacement questions. So, you know what? Let's just have you guys do 1 and 4 for now. Okay? I want you guys just do questions 1 and 4 right now. Okay? I'm going to put this bigger up on the screen. Okay? So you'll need the questions on your phone, okay, so that you can see them. Okay, so 1 and 4 for right now. Okay, let's have a look at these. So the first one's pretty easy. The position at 0 seconds. All right, well, it's a position versus time graph. Looks to me like at time 0 seconds, the position is positive 30 meters. Okay, and I do have to have the positive on there because there's negatives on the graph. Okay, position is a vector quantity. All right, at time 6 seconds. So here we are at time 6 seconds. So going over, so this would be 10, 12, 14, 15, negative 15 meters, I would say. And at time 14 seconds, so we go up to there, I'd say positive 25 meters. Okay, questions on those? That's just reading the positions off the graph, which is an important skill for question number 4. Okay, so it wants to know in question number 4, what's the displacement during these specific times? Well, displacement we know is calculated by going final position minus initial position. So it's going to require me to read the positions off the graph. So at time 2 seconds, my position is positive 50, and at time 4 seconds, my position is positive 4. Okay, so I would have 4 minus 50, which would be negative 46 meters during that time. Okay. Don't be afraid to ask questions if there's anything confusing you as we go here, guys. All right, between 4 and 8 seconds. Well, I already established what the position at time 4 seconds was. It's 4 meters, positive 4 meters. Okay, and 8 seconds. So 8 seconds is right here at that point. that looks like negative 33 to me, so negative 33 minus 4 should be negative 37 meters as a displacement for part B. Okay. Then between 12 and 16 seconds. So at time 12 seconds, position appears to be 20. At time 16 seconds, position appears to be 12. All right, so 12 minus 20, final position minus initial position, that should be negative 8 meters. Okay. Questions on any of those? All right. Now I would like you guys to try I'd like you to do number 8. So total displacement for the entire trip, total distance traveled for the entire trip, average velocity, and average speed. Okay, so we're looking at number 8 now. Okay, let's have a look at this one. So we're being asked to calculate 4 things here. All right, first thing we're being asked, total displacement for the entire trip. Since it's position versus time graph, my best bet for calculating displacement is to do this. Final position minus initial position. Were this a velocity versus time graph, I would do it differently. I'd have to find all those shapes. Okay, luckily, this is a position versus time graph, and the calculation is much simpler. Okay, so I need to find my final position and my initial position. My final position occurs at time 18 seconds. Okay, and it looks to be positive 4. Nope.
Negative 1.
I moved it, didn't I? I moved it. I put that whole line in the wrong place. Can you get rid of that line? That line sucks. There we go. Okay, so we're looking at negative 2, okay, as my final position there, okay, because that would be the x-axis. I'm just going to draw that on because it's very misleading. Okay, all right, so we got a final position here of negative 2, and my initial position is 30, positive 30. So negative 2 minus 30, okay, would say that I went negative 32 meters in total. Okay, everybody all right with that? Total distance traveled for the entire trip. Does that involve breaking this down piece by piece? Right, because it's scalar. I need to know how far I went in each part. So like the change in position for each part of this graph. So from this one here, I went from 30 to 50. So that's 20 meters. Then I went from 50 down to 4. That was 46 meters. Okay? And then I went from 4 to negative 42. So that would be another 46 meters. Okay? And then we went from 42 up to 20. So that would be 62 meters. And then we went from here to there, so from 20 to 27, so that's another 7 meters. And then we went from 27 back down to negative 2, so that would be 29 meters. Okay, so if we add all of those up, we should have our total distance traveled. So 20 plus 46 plus 46 plus 62 plus 7. Whoops, I hit a decimal, not 60. 62. Okay, plus 7, plus it was 29, right? Was my last one? I think. 210 meters, that sounds right. All right, that's my total distance traveled. And then average velocity and average speed. Have I done most of the work for those now? Okay, so to get average velocity for the entire trip, Average velocity is total displacement, which I already know, divided by total time, which I read off the graph. So negative 32 divided by 18 gives me 1.78, negative 1.78 meters per second. Okay, is my average velocity over the whole trip. Average speed over the whole trip is total distance divided by total time. I've already calculated that as well. 210, it's the same amount of time, 18 seconds. Okay, is 11.7, we'll say, meters per second. All right, questions on the position versus time graph stuff? Okay, have we done basically the same thing for every position versus time graph? We have. Okay, if it was a straight line, then we can bring y equals mx plus b into it. But if it's many sections, we always do the same thing. V equals d over t, final position minus initial position. Okay, it's always the same stuff. I can only ask you those things because that's all you can calculate off of this graph. There's no real way for me to twist it. Okay, that's just what there is. All right, we're going to have a look here at the end here at velocity versus time graph. So you're looking at question number 8 in your digital workbook there, and you'll see this velocity versus time graph. Okay, so you'll have that velocity versus time graph, which is what I'll leave up there, and it's wanting you to calculate the total displacement over the whole trip. That'll be a bit of work. Is that a lot of shapes? It is. Okay, average velocity over the whole trip. How do you get average velocity again? How do we usually calculate average velocity? Forget about the graph. How do I calculate average velocity?
Displacement divided by time.
Right, total displacement divided by total time. Pretty sure you'll have part of that after you've done part A. And then the total time, well, you can probably read that off the graph. Okay, and then some acceleration calculations, distance, okay, average speed, still total distance over total time. Right, so all things that you know how to do. Okay, there's just a bit of drawing and calculating in order to get to them. All right, so I would, let's say, get started on drawing the shapes, and then just for confirmation, I'll put the shapes on in a few minutes. Okay, if we're looking at the shapes, I think that's them. Okay, so you're going to have this rectangle, okay, right here, okay, that's going to be underneath. Okay, you'll have this triangle, this big rectangle here, this big triangle here, this even bigger triangle here, a little triangle here, this rectangle, this triangle, and that little triangle there, okay, would be the shapes I think you need to calculate the areas of, remembering that any ones that are below the x-axis have negative areas, so that when you're adding them together, okay, you're taking into account that displacement is a vector quantity. Right? It is 9:55, right? So we'll finish that one up after your quiz tomorrow, which will be on position versus time and velocity versus time graphs. I will post something this afternoon. Make sure you do it tonight. Okay, make sure you do that practice quiz, because I guarantee you it'll be worth it, okay, when you're looking at the real quiz the next day.